it's got a hard drive on there.
Yeah. So for the paper presentation, for the presentation part, we had 24 people, and I'm trying to squeeze that down into 6 days, right, for 4 days each. Our class is an hour and 15 minutes long, and while I would like to believe that we would fill that pipe up and one packet will be right behind the next, I know that is not going to happen. Right, we're going to have some kind of delay. So if you work it out, the max that we can do is 15 minutes, and that includes questions. So I would plan on your presentation being 8 to 9 minutes long, with 4 to 5 minutes of questions.
So the presentation is for the paper or for the project?
For presentations for your paper critique.
Okay.
So you're going to present the major ideas in the paper, and then you're going to present your critiques, future work. That's, some papers. I picked some pretty good papers, right? So there might not be there's anything wrong with this paper. It might be that, hey, if we build upon this technology, we could achieve X, Y, and Z, and this is how you would go about doing that, right? Which is the basis of doing research, right? You read a bunch of papers. And as you're reading those papers, you start to formulate in your mind how you would take the knowledge that you've gained at school and do it better.
And you said we can do one of the places we're working on now is our research? Or
Correct. It's so long as this deals with networking.
Okay.
Right? It is a networking class, so we got to do. It has to be networking. So like my research, I didn't have a networking research, so I was kind of just had to bite the bullet, right?
Are we actually writing a paper?
You're going to write a critique that I think I said it was, what, 3 to 4 pages? You'll write a critique, do a presentation, and that's part of the actual requirements of a graduate class, so that you have to write.
Is there a formal example of a critique that we
I would
can
pick,
follow?
so probably going to be ACM or IEEE. I would pick the conference format that you would likely target. So that, because part of the problem with writing papers, when you go up to, and you're actually trying to get your thesis published and your dissertation accepted, you're publishing all these papers, and it would be nice if you learned how to do papers now rather than at the end, so that you're not spinning your wheels, right, both trying to create the content and make it the right format. So I would encourage everybody, I know it sounds archaic, but I would encourage everybody to introduce themselves to LaTeX and start writing papers in LaTeX.
LaTeX?
Huh? Yeah, it's spelled latex, L-A-T-E-X, but it's LaTeX. And it is a compilable paper writing language. And if you need IEEE, you simply change it to IEEE at the top, and if you need ACM, you simply change it to ACM, and it changes all the fonts, the margins, everything into the right format.
How many times has that actually worked for you?
Well, so the beauty of this class is I'm not going to smash you for having the wrong format. Pick the format that you want. But a lot of conferences require that the paper is submitted in as a text, TEX document, and if that has to happen, then you might as well get used to it now. Don't have to. It's just a recommendation. If you want to do it in Word because it's easier, go for it.
How would you like it submitted?
I don't care.
What
So-
format for references does this college use?
So in IEEE, actually IEEE and ACM both have their own formatting, but they're very close to MLA. And by the way, LaTeX also does your reference for you, so you don't have to do any of that.
So it's the
That
same
actually, as bad as LaTeX is, that bibtex part of it really does rock. It just imports. You have a bibtex file, it just imports them and puts them in the bottom of your paper. Okay.
Is the paper including the other parts of our presentation, like the major points, or just the critique?
So I would include brief synopsis of the major points so that your paper is self-contained.
Okay.
So most papers actually have like a contribution section where they speak broadly of what they did, and then it's a whole bunch on how they did it. So your paper would be broadly speaking, and then you might need to include any specifics if you're actually found a critique of how they did it. They could have done it this way better. You know, if you're moving, you know, taking, like, let's say, what we're going to talk about today, right? Like this way to manage datagrams, you know, could also be used in virtual circuits or whatever, right? So just include enough information that it's self-contained. I'm going to read every paper that you guys do. I'm going to read because I'm going to have a really good question for you. And I would encourage the class to read at least one paper as we come up so that we have good questions for the students presenting, because presenting up in front of a peer audience is really hard, right? If you've gone to a conference, I've gone to some that were really easy, and then I gone to some where they just drill you. Like they're looking to punch holes in things, and you need to have answers. And it's obvious they spent a lot of time studying that paper and coming up with zingers, right? And so sometimes you have an audience where everybody is just happy to be here, and then sometimes you have some with a couple sharpshooters, and then sometimes you show up and they're all got guns and they're ready to kill you. So that's part of the whole, you know, for the guys that are getting PhDs, what you're really asking is to be a peer of mine and to be a peer of everybody, every professor in this building, right? So you're going to get punched a little.
Hazing.
No, it's not hazing, right? It's really like, I guess it would be like if you were interviewing a new employee and you asked them hard questions, is that hazing? Not really, right? Because they're going to work for you and you want them to know what they're doing. Right, for this, it's a little different. You're not going to be an employee for the PhD students, right? You're going to be a peer. And the question is, like, are you worthy of being a peer is really what it comes down to.
There's a website called Share lec8 that is pretty convenient. It's an online editor for lec8, and it's pretty easy to use. I recommend it.
How do you spell the first word?
Share, S-H-A-R-E, and then lec8.
Didn't they merge with Overland?
Probably.
Yeah, I was gonna say Overland. Yeah.
I think one of them bought the other.
Oh.
I'm not sure which one it was.
I think it actually started with a format, the TEX format.
TEX format is lec8.
And then the law part was added on, that had to add like macros and stuff.
Yeah.
Something like that.
It's really old and archaic, and everybody will hate it.
It's
So,
kind of like HTML, like where you use tags.
there are
Not actually HTML, but it had the same tagging concept. I didn't
yeah,
really
no
do-
closing tags, just kind of opening tags and brackets, but it's gonna be fun.
It's like if HTML was Turing complete.
Yeah, because it is a compilable language. Like the compilation is your paper, so it is actually tokenized. So
I think it's also Turing complete. I'm pretty sure it is.
all right. So we are on.
Oh, I guess I had one more question on the
Sure.
paper. So we have to do a PowerPoint presentation in addition to the
Yes.
paper itself? Okay.
Yeah, the PowerPoint presentation, rule for thumb for PowerPoint is you should have, besides your opening slide, you should have one slide for every 2 minutes. Right, so it's going to be somewhere on the crazy PowerPoint scale of 5 PowerPoints, right? I know, ooh, it's gonna be hard, right? What's really hard is getting up and answering questions, because people are gonna figure out right off the bat if you know exactly what you're talking about. All right, so we're moving on to networking. And the question is, why do we need networking? We just showed last week, or last Monday, that we could build a network and send packets across the entire network, and they are routed sort of across the network. and will arrive at one point and it will go from A to B, right? No matter what the network is. Why do we need routing then? Why do we need a network layer?
Assuming that spanning tree takes some time and it doesn't scale real well.
Yeah, so number one is it doesn't scale well at all. What happens every time you add a new machine?
Have to redo the whole reconverge.
Huh? So every time it does a new machine, that machine has to broadcast. Imagine every time you turned on your cell phone and you connected to the Wi-Fi, it sent a packet to every computer on the internet. You could see that it would be game over, right? You would basically DOS the entire internet instantaneously, right? And with the one single packet, right? Because everybody would turn on their cell phones at some point and they would be broadcasting. It would just be broadcast, broadcast, broadcast every time somebody went to a new network. What's the other reason?
If the source and destination belong to two different networks.
Two different networking. So when we talked about building this network, right, we said, oh, we can build this switch network, right, and it is gigabit Ethernet or it's Ethernet. But the problem is that it's just Ethernet. We didn't say, oh, this is a Wi-Fi on the other side, right? We didn't say, hey, this ISP uses Sonnet to connect point A to point B, right? These are different networking technologies. And different networking technologies, you know, we've talked about it through the class, right? How does Ethernet determine its packet size? It's by length, right? So if we have a different networking technology, then you're going to have different packet lengths, right? So what if you had Wi-Fi over here, which can send really ridiculously large packets, and it goes into Ethernet, which has relatively small packets? How do you break that packet down, right, and turn it into something that Ethernet can take? And then, oh yeah, you're communicating with another Wi-Fi device on the other side, right? Now we need to squish them all back together and send it over Wi-Fi. The headers are different. The packet sizes are different, right? Different networking technologies need some mechanism to interact with each other. So we have a scaling problem because, and it's not just with the discovery, right? We just have a scaling problem. So remember that so in addition to the broadcast, where everybody broadcasts, how else do we route tables through a network? We want to send a packet through Ethernet, just Ethernet from the link layer, right? And we have this relatively simple Ethernet, right? Remember I said, hey, there was a port here and a port here, and I think we did like one here, and then we did 3 on this side, whatever. That way it kind of looked like it just went to this switch, right? Right, well, so if you have machines A, B, C, and D, right, and then the network looks like that, what does the routing table look like if we want to talk to X, or X wants to talk to any of those? Let's say it's actually gone through, we did our broadcast and we built our tables, right? So X comes in here, and that's on port 1. So the routing table here looks like 1 and X, right? But what does this one right here, number 4, look like? What's in number 4, right? Number 4 has D, C, B, and A. Because all of these computers on the other side of this network are connected to that port in the way we described Ethernet. Now, what if you put 1 billion computers on the internet? These are going to be really long tables. And it doesn't make sense, it doesn't scale well. You'd have to have this ridiculous machine that had these huge tables with gigantic parts of memory, and they would be slow even if you were able to achieve that. So what we need is something else. We need to be able to make networks both interact with other networks. So we need an networking solution. And we also need to be able to route packets from one network to another network without that network knowing the entire rest of the internet. So no broadcasting, no nothing, right? How do we do that?
Address translation.
So well, we're going to talk about NAT, but right now we're just trying to get to IP, right? The solution is actually IP.
So
And most of the people are,
what was the first one, the second one was rockets, the first one was it?
the first one is scaling. So scaling, there's a scaling problem, and we also need to be able to do internetworking. So, because otherwise our switch tables are going to be ridiculously large. Every time somebody connects to the internet, I can't imagine how many times a device gets turned on and off on the internet right today, right? But could you imagine like getting a packet from every time somebody turns on a machine, right? It's crazy. It would take, I mean, presumably desktops could remember, but mobile phones don't remember. You go from one tower to the next, right? Or you're going from Wi-Fi to 4G. So there's just a lot of rediscovery that's happening. And so we need to be able to route information from one side to the other. And then we manage our internal networks on the link layer.
Mm-hmm.
And because on a small scale, the link layer is much more efficient. But for moving from one network to the other, you're going to connect through your ISP to the internet. We need something else, and that's in the networking layer. So the other part of the problem is with spanning tree, we saw right off the bat that it doesn't always come up with the most efficient route. And then if a route becomes less efficient or breaks, so we talked about routes breaking and going through spanning tree again or whatever, right? But so you could use that on like a less efficient route, but then you're like turning the network off and turning it back on every single time you want to find a new route, right? So like, so let's say that there's a direct hop between this, right? And for whatever reason, this thing is slow and this thing is faster. It would be nice if we could keep both of these links alive and then use the fast one most of the time until it starts getting congested and then use the slow one. So we'd like to be able to do efficiency through the network as well. And this is really important across the internet because the internet is a really large network. So we would like to be able to do that. So it comes down to we need to scale, we need to have heterogeneous networks, and we also need to be able to do bandwidth control, right? Be able to make our network as efficient as possible so that we're filling all the pipes up. So, what we are going to talk about first is packet forwarding. And we will understand how a packet gets forwarded from one network to another. And then, after we understand forwarding, we're going to build a concept on top of that of routing. Because forwarding is routing without thought, right? We could design any network ourselves, right, in a very static way and simply forward packets, not make any decisions. Routing builds an idea on top of that we can change the network, or the network can change itself independently, so that we don't all have to coordinate together.
So forwarding, we'll work with the static routing.
So think of forwarding as static routing is a good idea. So without the table, we're going to just forward. So imagine you don't have routing at all. But for those of you that understand static routing, you simply put in, you manually put a table and it says go here, go here, go here, go here, right?
Mm-hmm.
But forwarding doesn't even have that table yet. Right? It's just, we're going to build on the idea of just moving one packet to one network to the other.
Okay.
So in order to do that, we need to kind of talk about services first. Services is actually part of the transport layer, but in order to understand why we're going to build this network, we need to really kind of understand that there are two different types of services that we need to accomplish. Because understanding those services and what we want to do will actually make us make intelligent choices about how we build the network. So everything that we have talked about, other than talking about, in the first of the class, we talked about like old-fashioned telephone switching networks and stuff like that. And inside of the switch is actually a switching network also. But all the other stuff we talked about, really, we're talking about datagrams, right? We're talking about taking a chunk of data and moving it from one point to the other. There is no electrical connection, solid electrical connection like the old-fashioned telephone lines.
Mm-hmm.
Right, so we're moving a datagram from one network to the other. And the thing about datagrams is that if we have a datagram here, and we'll call this one circle 1 and circle 2, right? And it's going to go through this network, right? One might go this way, and then it might come up here and go through this fast line, right? And 2 might go through here and then go through this slow line. Because it's really, they're all independent of each other. We send a packet and it goes through the network and the packet finds its own way. So the packet finding its own way, this is a connectionless protocol. Skipping it a little ahead, like the most popular connectionless protocol is what?
IP.
UDP.
Email.
UDP, right? So, right, we're just going to span something off the network. And there are reasons that you would want to do that. The other one is we want a connection. We want to talk with another computer much like we used a phone line. We're going to establish a session and we're going to decide what that session is. So now we have, let's do square 1 and square 2. Right, so square 1, so remember this was a datagram that was going through the network. And then in the same communication, like the second datagram goes a different route. And they may or may not arrive at the same in order. You understand, if they go different paths in the network, there's a decent chance that they won't arrive in the same order. In a modern network, they're really efficient and the chances not as great as you think. But datagrams assume that they won't. So, but in a connection, right, when we're talking over the phone, our virtual phone lines, what we're really trying to do is when you talk across this virtual phone line, you guarantee that packets arrive in order. So we don't have to worry about reassembling out of order packets. And you guarantee that in order to do that, you guarantee that each packet goes across the network over in the same line, the same direction. It goes the same path. So how do you do that? Right? So you need some kind of communication channel to be established through this network. And once you establish that communication channel, you talk through that network, and presumably, if you're playing fair, you build the communication channel, you exchange data, and then you jointly tear down the communication channel. And we'll talk about in the security part of not tearing down that communication channel. And so when we do this, really what we're doing is to move packets across the network is exactly what we were talking at Ethernet last week, or on Monday, was that we do store and forward packet switching, right? So a packet arrives into a switch. The switch has like an input buffer and an output buffer. And explain this a little bit. We conceptualize it like this, but it's actually split down the middle and opened up, right? 1, 2, 1 and 1 are the same port. So, but you conceptualize it like this, right? Where you have a fabric in between, and the input buffers and output buffers are there simply because, like we talked on Monday, you know, 1 could talk to 2, and then what happens if 2 talks to 2, or that's probably not a good example, 2 or 3 talks to 2 and 4 talks to 2 all at the same time. And if you do that, then the packets are actually arriving at the same time, and they can't be pushed out the network fast enough, right? So you need some kind of a buffer to hold it. And it's really just memory that just lines the packets up to forward them on. So the big question here is, what do you do when the buffers are full?
You have to tell them.
Shut up for a while.
So, yeah, we just drop them. We drop packets.
You drop and send the feedback, right? Telling the sender that window size is 0, meaning that my buffer is full.
It could be a scheme, but the simplest scheme is just drop.
At what point does it just, this isn't arc spoofing? Or arc spoofing, is that why it spits out all frames on all connections?
Yeah.
At what point, because this seems like that'd be a prevent that, right? If it just drops all packets, then you wouldn't have arc spoofing.
So the simplest method is drop the packet, but there are other methods to do it. And the question is, if you're going to drop a packet, which one are you dropping? Are you dropping the one that like was the straw that broke the camel's back, the last one, right? Or are there other less important packets that you want to drop out of there? There's a lot of choices that you can make. Is the switch or router responsible for saying, hey, I'm full, right? Or do you rely on upper layer a protocol like TCP or UDP, which we're going to program to manage these drop packets, right? Because the transport protocol is the reliability piece in the network, right? Even though this is really, really reliable, modern networks are really reliable, but is why they are reliable, it is the transport protocol that's responsible for packets arriving or not. So instead of drawing that out, right, you'll often see like diagrams where it is simply something like this, right? You have ports, right, and this is the input buffer, and you have some amount of it filled. And this technically is a first in, first out buffer, right? But you could have queuing, you can do both. We can do whatever we want. We're building the networks, right? So let's take a look at forwarding. So this is not routing yet, right? This is just forwarding. But this is forwarding between networks. To give you an idea of what we can start to do. Right, if we're gonna forward between networks, let's assume that we've solved the problem that there is a box that exists on the network that's responsible for forwarding. And we want to forward packets from one network to the other. And presumably, if we land in that network, it will know that we're where we're supposed to be, and it will be forwarded on to, in what we talked about on Monday and Wednesday, on just forwards to the network, right? So if we want to forward a network, it looks a whole lot like what we did looks a whole lot like switching, right? If it comes in 1, it goes out 3. If it comes in 2, goes out 4. If it comes in 3, goes out 3. Or that's bad.
2 or 1.
2. No, but I want to do, if it goes in 4, it goes in 2. Right, and if we had this, right, where this is 1, 2, 3, and 4, then there is a virtual connection here. 1 goes to 3, and
2 goes to 4.
2 goes to 4, and so on and so forth. But then let's build this actually in where not only do we have a number of routers, but we also have a number of ports on those routers. So instead of doing this, let's have table 1, table 2, table 3, and table 4. And then let's put a number of ports on those. So A could be this one could be like port A, B, C, and D, and then that goes to some other table, right? So let's have let's leave A by itself, B, E, and F, or something like that. So, what would a BB mean?
That's itself.
We've arrived at home, right? It's somewhere on this network, right? And then should have kept the numbers and so on forth, but what I wrote down otherwise had letters. So so A maybe A doesn't go anywhere, right? A has no route. B say the BB goes to the network. CE goes routes from C to, or forwards from C to E, and D forwards from D to F. So we could build tables so that where we had something like where this is the input and this is the output. So not totally different from what we had with switching, but the deal is that A can have like no destination, or A talks to itself, right? That means that we do not forward this packet. We're in the right network, right? The input of B always goes to C. The input of C always goes to F. The input of D goes to E. The input of E goes to D, and we can start building a crazy network, right? Where inputs are redirected to other networks. The problem is now is we can interconnect networks, but we haven't solved any of our other problems. The other thing is this is all well and good for datagrams, because a packet arrives and we simply forward it. Packet arrives and we simply forward it. So, and it's just a table model of where we route that packet to. Not route, forward that packet to. The problem is that method does not work if we need a virtual circuit. If we want to imitate a telephone line or some other thing where we're having a connection-oriented protocol where we want to communicate with another computer, and that computer communication is bidirectional and it is for some set amount of period of time. Remember that switching networks are good for, like, hey, we're going to have a conversation, and when the conversation's over, we're going to hang up. So in many data programs, you're going to download a file, right? Files, ironically, if you're going to watch a movie, that's actually almost always datagram. The reason being is because you can lose some packets and it'll still be okay. If you're going to download a file, though, losing parts of the file is not okay. It almost, in almost every circumstance, it will result in the file not even opening, right? And even if it does, it's going to be corrupted and at the very least missing some information that was presumably important. So in those kind of communications, we want to have a circuit where we do an exchange of information, and that exchange, when we get to TCP, is like, hey, I got a part of a file. Hey, I got a part of a file, right? One person is sending, the other one's acknowledging that they're getting what they're sending. So we want to open up a circuit. So if we're going to have boxes between networks to have circuits, that means that the boxes that are interconnecting the networks, which we're going to call routers later when we actually build up routers, need to be able to remember which circuit is which. So the datagram model does not work because there are multiple paths through the network. And in a connection-oriented protocol, it depends on that path through the network always being the same. So routers, or these boxes, need to be able to remember what circuit they're on. So the first thing you do to create a virtual circuit is send a datagram saying, hey, I would like to, is basically ringing the phone. I would like to have a communication with you. And then the other one sends a datagram back, said, great, let's establish a connection, and then we connect, right? So then we have computer A, and let's, tired of drawing squares. Wants to talk to computer B. Right, so they find a way through the network that's acceptable, and then they establish a connection. And when they establish the connection, the difference between a datagram is that all of these points, so let's call this 1, 2, 3, 4, and 5, need to remember, at least the 1, 3, and 5, need to remember that this is the circuit. So they can no longer, even if these are all interconnected, and there are many paths through this network, that they always choose the same path. Otherwise, we run into serious problems of things arriving out of order, things getting lost, blah, blah, blah. So now our new requirement is these special boxes are remember which circuit that they're on. So in order to do that, it's not all that complicated, right? You get a request for a circuit, and you can see the packet coming through, and you say, oh, this is a request for a circuit, right? My routing table says, from whatever, well, we're going to learn quality of service and different routing protocols, whatever, but the router knows what the likely best path through the network is. And so that likely best path is 1, 3, right? It's going to forward to 3. And then we simply label this thing. So let's call it like lowercase a. And then it arrives at 3 and it says, hey, I think the best path through the network is to go to 5, right? So this is 3, 5. And we'll just call this A. And then this is 5B. And we'll call it A for right now. But notice that these are all doing this independently. They're not, this router is not communicating with this router. So it doesn't need to be AAA. All it needs to know is things that arrive from 3 that are labeled A. Well, that actually, I call that C. And then things that arrive from
C.
yeah, things that arrive from 3 that are labeled C, I call that X. Doesn't really matter, right? They invent their own numbers. All they need to be able to do is keep track of them. And in the middle of the internet, they need to keep track of a lot of them.
So all this information is being appended in the buckets, right? As it's being sent. Like
Yes.
between 1 to 3.
Yes.
So that they will have a.
Yes. So right now, we're just going to say it's appended in the packet. We can discover other ways that might not be appended in the packet. Right? We could use port numbers and all sorts of other things to keep track of what is what, right? But for right now, let's just append it in the packet. And so doing that in the MPLS, so remember we talked about these big fiber pipes inside of the internet backbone and ISPs, right? And they're single mode fiber and they run point-to-point protocol. We actually did an example of point-to-point protocol, and they can set up these virtual circuits, right? And so now we have some network over here that we've actually described now and we can build. So we're reducing the size of our cloud, right? And inside of the network, or the internet, right, we have some ISP machines. And so that ISP routes these connections across the internet. And by the way, it might, because SONET is remember we said SONET is a virtual circuit, right? We didn't have, ever when we talked about point-to-point protocol, we never described that as a datagram, right? It is a circuit. So now, we also need to be able to route datagrams across an actual circuit to arrive at the other side and turn it back into a datagram. Sometimes those datagrams might also be turned into circuits, right? So if you want to take a look at an actual protocol, and it does exactly what you said, which is append some data. You get an IP packet. The IP packet looks like so IP packet looks like, has some IP data here, and then it has a CRC here, so that's the header and trailer of IP, and then it has TCP and data. The problem is when this thing arrives at this new network, the network needs to be able to move it from one place to the other. So it does exactly what you said, which is add some stuff to it. What's it add to it? Well, we already have IP and TCP. When you take this datagram packet, which is connected oriented protocol, but it's still coming across the network as a datagram, right? and we need to be able to move it from this box to this box in a real actual circuit. So we just append the information needed to do that. So one of the things that we append to it is point-to-point protocol, the header for that, which is all the information needed to do that. And then in this particular example, the middle append is MPLS, multi-protocol label switching, which is totally unimportant. Just doing it because it's a real example. Right, so it adds this stuff to the packet when it arrives here so that the packet arrives here. And that's all it does. And then once it arrives here, it just destroys it. And then forwards the original packet. This actually gives us a good idea on how we could route things through the internet, through different layers of networks, through totally different types of networks. Right, is that if we're able to just add stuff to move from point A to point B, right, and then remove that, and now we need to move from point B to point C, we can simply add stuff again. Now it might be that we can move from point A through B into C without removing anything in B, right? But the idea that if we can just change our packet, not the contents of the packet, but just append something or prepend something to the packet to make it move from one point to the other. Now we got the actual inner workings of being able to move data through disparate networks. The networks no longer need to be the same because we'll append and sometimes, or prepend, sometimes append the packet so that we can move it from point A to point B. And if we can do that, then we can set up any situation to move that packet somewhere else, so long as it's the same size. We haven't talked about dividing it in half yet. And now we can move it anywhere. We're not necessarily efficiently, but we can move it through any type of network. So this is the actual basis for internetworking. How we make networks that are totally different, designed different from the physical and the link layer, actually play together well with each other. But it does lead to a cost. And that cost is, in order for networks to play well to each other, then there has to be one protocol in our protocol stack that they all share in common. And most commonly, that is IP. So there are other networking protocols of IP, but understand that in order to move one packet across the network to another packet, there has to be, or move one packet across the network to another computer, there has to be one protocol that they, at least one protocol that they share in common. Otherwise, how do you do this? How do you move across the network? If you had a network that we designed from the ground up with and it didn't include IP at all, how do you move that data across the network, which we're talking about the internet? No, HTML, it's still IP. It's just an application protocol on top of IP.
We can have upper layer that take care of that.
Oh, we can build all the upper layer protocols we want. It just understand that if you want to talk to another computer, at least one protocol has to be the same. So in the internet, routers communicate on IP, which is why IP is very difficult to upgrade. Because IP kinda needs to serve the lowest common denominator. Let's say that we have one network that has a you guys read a paper and he came in, it's like, I got the best quality of service idea ever, I read it in this paper and I'm gonna go off and make $1 million, which isn't gonna happen because you're gonna publish your paper for school, right? And so you have this network, right? It's like grade A network, right? A+ network. Quality service, it's highly efficient, blah, 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 blah. Right? Unfortunately, you want to talk to computer C over here, right? And it has to go through the internet. And right now, let's just treat the internet as 2 boxes. The problem is if you're communicating over IP, all the quality service stuff in the world, if it doesn't exist in IP, it's not going to make it to C. Because quality service is a property of a network, and you don't own this network. So basically you have to, well, inside would be great. Basically you have to downgrade to communicate outside. Now that in IP, I can tell you there is some quality of service built in, but quality IP really has to serve the lowest common denominator. So whatever is not in IP, right? It might be IP itself might be the problem. Even if C was on an A+ network too, A1+ network, right? It doesn't matter, because quality of service is dependent upon all the machines in the network.
So we cannot control the internet for the quality of service?
So it has some quality of service built in to IP, because we're now in IP version 4, right? And so they have fixed some things. And there's a lot of stuff in IPv6, if we ever use it. There's a lot of neat security stuff actually in IPv6. The problem is we have to decide to all use it. And I can tell you the very one certainty in the world is if you make the statement, if everybody would, you've already lost. Right? You need to be able to come up with solutions. If I do this, this will happen. And it doesn't depend on forcing other people to do it, because it's never going to happen. So this might be the better point for actually doing PowerPoint, so I don't have to draw these giant diagrams. Let's take a look at this. Let's just list it out on the board, because it's not important where it is.
So if we're on IPv4, how did we convince everyone to get to IPv4 in the first place?
Attrition.
How did we get to IP?
IP version 3.
Yeah, everyone's on IPv2 now. Everyone's on like how do we get?
Because redefine everyone. So how long we've had IPv4?
So like
forever,
when we made
right?
it
Before when we said everyone, it was like 23 universities, right? So now you're talking of literally a billion, at least a billion devices, right? Probably much more than a billion devices. We actually talked. I got the number right. It was 16 billion, right? 16 billion devices. They obviously don't have IP addresses because there's not that many to actually connect, right? That's why we'll get to NAT and all that other stuff. Mm-hmm. But IPv4, the biggest limitation that's right there in front of your face, besides all this quality service stuff and whatever, is 32-bit address space, right? We have 2 to the 32-bit address space to connect everything to the internet. Well, or it just told you that there's 16 billion devices, but there's only 1 billion addresses. So how do we do that? And that's where NAT will come in.
That's the reason why we don't go to IPv6. It's because of NAT.
It's because of NAT.
Yeah.
Yeah.
Well, if you're lucky enough to have one of the public IP addresses.
Everybody has one.
Companies
Otherwise, you're not connected to the internet.
Companies.
But it's actually much less than 1 billion. I mean, we say there's 1 billion addresses, but because of the way it was actually implemented and because it needs to be backwards compatible, there's much less than 1 billion, right? Because addresses that start with 0, like a Class A network, that means that it can't be subdivided, right? And then addresses that start with the bit 1, which is a Class B, that can't be subdivided, and then Class C, which starts with 1 can be, but you already just took off, you divided by 2 twice, right? So you're down to like 250 million addresses. So it's much worse than just 1 billion addresses.
So going back to the IP, how the communication would happen between a network that's running IP and another network running like Apple Talk?
So network that's running what?
Running IP protocols and another network's just running Apple Talk, which is 2 different.
So the question is, can you take Apple Talk and run it across the internet?
Yeah. Or how?
Anybody think that they could take Apple Talk and run it across the
Can we run
internet?
just like an Apple layer that translate from Apple Talk to IP, then IP?
So you can have, so there are ways. So you're gonna run Apple Talk, right?
You could package Apple Talk inside IP.
Yeah, exactly.
What you would do is you would do something really convoluted, right? You would encapsulate Apple Talk in IP to move it from one place to the other, and then have some service that unencapsulates it and spits it out into the other network, right?
Okay.
And when you're doing like virtual private networking, you do all sorts of crazy stuff like that. Make you just seem like you're local, right? You can make it seem like you're the only 2 computers in the universe, right? There's all sorts of things that you can do, but you're still using IP.
So it's kind of tunneling the IPv4 of the IPv6.
Well, so you could also do this. You could do you could have IP. You could establish a circuit, or a virtual circuit, right, and then pipe things through it, right? But you're still encapsulating it and it's sending it across, right? So, what are some of the things that we would need in? Let's talk about IPv4 because we're eventually going to talk about all these things because we're going to go really in depth on IP. What are some of the things that we need in IP? So the biggest one that should be shining out in, for everybody is source and destination. We need to be able to move, and we need to be able to find our way back. So to move forward, we only need a destination. But to move backwards, we need a source, and presumably we need somebody to talk back to us, right? What else? Port. We need a port. What do we use ports for?
It's kind of like an interface to the next upper layer.
Yeah, so we talked about it.
Sort data.
Yeah, it's just really to sort data. So because a client talks to a server really needs to kind of have an assigned port. So for like HTTP, we just say that's 80. Sometimes it's 8080, right? But it's say, hey, this port is this. Is it possible for you to make a Linux server and put SSH on port 80?
Yes.
Sure, absolutely possible, right? Ports are totally, but you can do anything you want with a port, right? But by convention, we say, hey, these ports are this, because if a client is going to talk to a server, then it needs to know what port to talk to, right? So we also have, so this is source adder.
So technically, if you were implementing something though, and you did like override traditional ports like that, that would essentially make you more secure, right? Through obfuscation and
Yeah, it's like, yeah.
Only until somebody figures out what ports you're using.
right.
So,
It's not lots of security.
so the port though, and we talked about this right at the beginning of the class, the port is not in the IP layer,
Yep.
right? call this IP. You do actually need the port, but as in the transport layer. And really, we call it a higher level layer, but when the packet comes along, it's actually the bottom. And there'd be all sorts of things that we need for TCP down here. But one is the destination port, and one is the source port. Because when you talk to port 80, you don't leave port 80, right? You leave some random port. And so the server needs to be able to talk back to you on that same port because that's the one you're listening on.
So how possible is it to overwrite like port 80, for instance? Because it's already there. If you have to put anything on port 80, then that means you have to change the entire scope of that.
Well, let's say you had a server that it wasn't a web server. If it was not a web server, you don't need port 80. So you go to Etsy services and you override port 80. Do whatever you want. In Windows, you're going to have to go jack with the registry. But in Linux, it's simply a text file. You just override it. Boom. It's just like that. Right? So this is transport. Not a bad idea. We do need ports. It won't work without ports. But in order to just route packets, let's say we only had one service on both ends, right? Then presumably we don't need a port, right? So, what else do we need put in here?
TTL.
MAC address.
TTL. What is a TTL?
Time to live.
Time to live. Why do we need TTLs?
If a packet gets lost, you can just like live on the internet forever.
Yeah, yeah.
Nice.
Packets can, if you didn't have a time to live, a packet could live on the internet forever. Until it ran into a thing that was full and it finally got dropped, right? But time to live was meant to prevent that exact problem. So you have this network, right? And while it's not fully interconnected, it's really connected, right? So what happens if one of these things that are connected, somebody hacks it or somebody misconfigures it? I don't know which one happens more often. They happen all the time. But for whatever reason, right, we get a loop. It's going from one, like let's say that we had a table that was A forward to B and B forward to A. Right, it was simply back and forth, right? So it's a loop, but it's just over one wire. It's bouncing back and forth. That packet would be there forever. So the time to live is a value that we put in here to say, hey, when this reaches 0, drop the packet. I don't care. And this is a neat way of actually mapping out networks, is putting time to live packets in there. So, time to live, right? And so what happens every time it passes through a router, the router actually reaches in the IP header and decrements that value, forwards it on. Because it's not really, well, it's a packet, but I mean, really it's just a set of bits, right? And it's moving through a computer. Changing things in it isn't hard, right? Simply look in this place, it's in the same place every single time, and just read that value, decrement it, write it back. What else? Huh?
MAC address.
FLAG.
Oh, flags. Yes, we need a number of flags. And in here, I think, we'll talk about the actual flags, but we'll need a number of flags. One of those flags would be like, oh, this thing is fragmented. Remember, we moved from a network that has big packets to a network that has little packets, right? If it has little packets, then we need to divide them in half. And that means that we need to take this thing with all this TCP data down here and actually divide it up into different parts, right? Put them in new packets with addresses and destinations and time to lives and forward them on, right? So let's say like one of the flags is fragmented. Well, if it's also fragmented, right, then we also probably need a field to say, hey, what fragment this is. And then we also need a field to say, hey, this is how big it was supposed to be. So like, a total length and a fragment. What else?
About a version identifier in case
Yeah.
we check it later.
Yeah, I can tell you what what's the version in this?
4.
4. But it is there, and it's the very first thing in the pack. Version 4. What else? Ironically, they were very optimistic because it looks like they have like 8 bytes reserved for that version. Or maybe it's only 8 bits. Still.
4 bits.
Huh?
4 bits.
Is it 4 bits?
And they're optimistic.
Yeah, even 4 bits is optimistic. Pretty sure that we may get to 6 at one point, but probably never changing after that. So, whatever other things can we put in there?
The error, like, so.
Yeah, we need to have some kind of error detection. Whatever that is. We actually said what error was in IP. We said it in class.
CRC.
Checksum. Terrible error detection. It's there. Anything else? So in the book it has this. Differentiated services. What is that? It's your little tiny field that is, I'm going to count them out this time, it is 8 bits. That
It is 8 bits.
It is 8 bits to do quality service. That there, folks, is all the quality service that you're getting in IP.
Don't use it, it's a pain in the butt. I'm doing stuff with it at work. So don't.
What else? There's actually one more we haven't talked about.
You have the, you need to know what the next layer is, so isn't there a flag for whether or not it's TCP or UDP or something?
Correct. So there's an ID. It's like right here. And this is basically, the problem is, if transport is managing like connection and so on and so forth, then in order to pick the right path, and I think I drew this on the board, right? You have the bottom layers. We look at our stack, right? It's the physical, the data link, network, and transport, right? But the network layer is what we're talking about is IP. All this stuff down here doesn't matter what it was, right? Because it's coming up, but all roads lead to IP, regardless of where they came from, right? But here, not all roads lead to whatever, right? We could have HTTP up here, which is part of TCP, right? And so IP needs to, when you're coming up the stack, the machine needs to know, instead of doing this deep packet inspection, is there a quick way that we can look to say, go that way and do and give that to TCP, right? And so IP and TCP have identification fields to say, to give the computer a hint which way to go on that path. And so we have an IP field. And that's about it. So,
did we have the upper layer protocol, like a field for that one, so the IB would know which protocol that should go?
yeah, that's the ID.
That's the ID?
That's
Oh.
the ID.
Okay.
It's called the identification, but in our example, since we're talking about TCP, right, it would be like a flag for TCP.
Okay.
It's not a flag, but it's a integer value. get on more with it later. So we're gonna spend a little time in IP, because IP and TCP are the most practical examples of networking. They're the things that you will probably do the most, with the exception of maybe you, who's gonna have to get a little bit lower in things. But we're gonna spend some time.
About UDP. We're not gonna spend any time in UDP.
Oh, we are?
Oh yeah, no, we'll do TCP and your programming project is UDP.
UDP is really slow. Like you stick some ports on there and a couple flags and that's it.
Oh yeah, unless you have a guaranteed delivery.
Oh, yeah, but that's something you implement on top of UDP. The UDP protocol itself is really slow.
Yeah.
Yeah.